So thank you for the invitation. Okay, so my title is an arithmetic refinement of homological mirror symmetry for the two torus, and this is joint work with Tim Perutz. So I pushed really hard to have this paper on archive, but unfortunately my collaborator hasn't finished it yet. So I hope it will be up in a week or two. But here is the talk. Okay, so here is the setup. T2 is the symplectic torus. It has a symplectic form. And we have a fixed base point on T2. So, and a primitive of this symplectic 2 form outside of this base point. So we have this, the data consists of the torus itself, the symplectic form, the theta, and the base point. And finally, there is a line field that I'll suppress. So this is an important part of the data, which is important for the grading, but I'll suppress in this talk. Okay, so. Huh? It's a real line field, and so okay. So all right. So we have this data, and associated to this data, I'll describe something called the Fukaya category. It's going to be a relative Fukaya category related to this divisor Z. Okay. So this is going to be one side of homological mirror symmetry, and well, I should also say that we have to pick a base ring, and in our case, this base ring will be, crucially, it will be the power series over Z. Okay. So, so this is a category defined over that ring. What's the other side? So the other side will be what's known as the Tate curve. So does this move? Yeah. Okay, Tate curve. So this is an explicit algebraic curve. It has this equation. Let's see if I remember it. And A4 is this explicit thing, and A6 is this explicit power series. Great. So it's a little exercise, if you wish, that 12 always divides this, and this is a curve. So I'm just writing the affine equation, but I'm considering it as a projective curve over, again, Z adjoint Q. Okay. So additionally, here we have additional data as well, which is one is a point on the Tate curve, this point at infinity, and another thing is an explicit isomorphism from H1 of O to K. This is an invariant differential. It's explicit choice of differential. Okay, so we have this two. So there I started from the symplectic torus, and here I started from this explicit algebraic curve, and then here I construct something called derived category of perfect sheaves. All right, so the statement that of homological mirror symmetry that we prove is the following. So suppose so a choice of basis alpha beta of H1 of T2 determines a functor from this symplectic side, this Fukaya category, to the algebraic side, this perfect sheaves, and such that after derived closure, so derived after passing to the derived level, we get an equivalence. So it's really, at this point, it's really an alarmingly abstract statement, and it's not clear what we actually prove. And well, this again, I have to emphasize this is over ZQ. So my goal for this talk is to remove all these abstract definitions, just and cut down to actually what one needs to prove. And then I'll try to explain. There's a very explicit computation one needs to check, and then that's where we are going to go.
So does this equivalence tell you anything new about either side?
Anything new about either side?
Yeah.
Well, I mean, so one thing is, it's already well. I don't know how should I say whether it defines anything new about either side. So somehow, let me get to the explicit equation, and then you'll see maybe what it shows us. Okay, so I should make a remark that homological mirror symmetry, especially for the true torus, has been around for many years now. And well, the differences of the main point of this talk is that the previous versions were defined was such an isomorphism over something called the Novikov field, where the Novikov field is a kind of a power series, like so, where AI are complex and Ti are real, and well, Ti goes. So I don't know. I don't have to be precise here, but what I'm saying is that we define this category. So both sides are defined in this much smaller ring in some sense, and there is a refinement. There's an integral information that's part of this isomorphism. So another way to say is that this isomorphism doesn't follow the one that's known over the Novikov field, but from this you can easily obtain the statement over the Novikov field. Okay, so maybe I should write the names for who proved these kind of things. So it's been proved many times by now. Certainly it was also Kontsevich. Okay, so in this, in a precise sense, our result is a refinement of the known homological mirror symmetry. So let me start by sketching the definitions of either side. So what is the Fukaya category in our case? So the objects are Lagrangians. So these are closed, embedded, exact Lagrangians in T2 minus 2 point. So this is a very complicated way of saying the following. So these are simple closed curves. So let me say like this: every non-trivial homology class of simple closed curves is represented uniquely up to Hamiltonian isotopy by an object. Okay, so the objects are extremely simple. We are in an extremely simple symplectic manifold. So here is T2, and then here is a point, and my objects are sort of curves like this, and curves of different slopes. So these objects are enhanced, in some sense, enriched by something called brane structure. So they have to have a spin structure on them, and they have to be oriented. Again, I'll suppress this because this is related to, in some sense, grading and science. Okay, so far I'm just kind of repeating the general construction in the case of the torus, and so exact means, so remember one part of our data was, so omega was d theta on T2 minus z, and exact Lagrangian means that theta restricted to L is exact. But really, I mean, I just already described all the objects. So these are curves, and then they can, if you fix your theta, they will be represented by explicit embedded curves up to Hamiltonian isotopy like this. Right. So, all right. Objects are.
With this exact condition, you don't have too many Lagrangians left.
Yeah, there's.
Just one dimension. You get 2 dimensions.
There's for any slope. So as I said, for any slope, there is a curve. Right. So for any curves, homological classes on H1 T2 is represented by their slopes, and then for any slope, there is a exact Lagrangian up to Hamiltonian isotopy. Okay. What are morphisms? So people who have seen this will be bored. But so if I have 2 Lagrangians L and L prime, so 2 such curves, the morphisms homes between them are given by Floer chain complexes. So this is, in other words, this is over the field K, it's just the intersections of L and L prime. So if your L is not transverse, then you make it transverse, and then these are the morphisms. So this morphism space comes with a differential μ1, which is the counts of holomorphic disks like this. And furthermore, there is as usual, there is higher products. So maybe let me use this other board. So I can count holomorphic triangles, and then this contributes to μ2, and then in general there is polygons, which contributes to μ3, and so on. Okay, so let me discuss what's easy in the case of torus. So again, we are in this very simple symplectic manifold. So as I said, objects are represented by these curves, and I can always compute Hom L prime as written. So this will be the geometric intersection number. I can put L and L prime so that they don't bound any bigons, and then the Hom space is extremely easy to compute. μ1 in that case would be 0. So this is also easy, and μ2 requires a little bit of work because you actually count some holomorphic curves. But still, if you go into the details of this transversality and so on, μ2 is also easy. So given given 3 objects, if I want to compute mu2, I'll compute some explicit polygons on this on the universal cover, and then so I can do that. The hard part comes in when you want to compute these higher products. It turns out in this case there is transversality problems, even in this simple case. So this is one thing that we worked out a couple of years ago. For example, we were computing some mu3 product that involves only these 2 Lagrangians. And then it turns out there is non-trivial mu3s that map exactly to this point. And then you, somehow the transversality fails, but one can prove by deformation arguments that there is essential mu3. Okay, so we did this before. So so this is the base point. So in general, this higher products are not, even in this simple case, is not an easy thing to do. Still it's not a combinatorial object. All right, so I tried to sketch very fast. Oops, what did I do? I tried to sketch very fast an explicit A infinity category. So I started from this data T2, Z, W, theta, and well, I described you explicitly objects, and then I told you that there is some A infinity structure, and we can compute some part of it. So let me make a remark about the base ring at this point. So here is a simple example. So suppose I want to compute, so let's say, so this is a part of the universal cover of the torus, and suppose I wanted to compute a triangle count between this horizontal Lagrangian, this vertical Lagrangian, and this diagonal Lagrangian. Okay, so one thing that you immediately realize is that so these are so how should I say? So if I fix so here is one thing that I want to count. Mu2 of alpha beta, it will be some number of counts times gamma, where alpha beta are 2 corners, and gamma is this third corner. Okay, so when I try to do this, I see one triangle here. So that's great. That contributes. It's a holomorphic triangle. It contributes 1. But you will immediately realize that there is this other triangle, this bigger one, that has exactly the same corners, and so it will also contribute. So there is another triangle like this. And if you think just a minute, you'll see that there's infinite many of these triangles that will contribute to this count. Okay, so I mean the fix is in the standard theory is to use this Novikov field, and you weigh the count of polygons by their areas. And once you do that, you separate this count, and then you can actually make sense of this count. Okay, so here what we do is instead we put a base point. So this is kind of not an original idea. It has been around in many contexts, and notably in Hegardt-Fleur theory, that when you count these holomorphic triangles, you count them, you weigh them by their intersection with this base point. So for example, this one has 0, this one has 1, and this bigger one will have, I don't know, 3 or so 4 or something. Okay, so in that way, we replaced. So we have a well-defined category over Z adjoint Q. So, okay, so this is the symplectic side. So, in the symplectic side, we can define the Fukaya category over this ring. Now, what's the algebraic side? So, I mean, for those who haven't worked on this kind of stuff before, I should maybe make this trivial remark that it's important to keep this A infinity structure as a chain level structure. So this is, we are not allowed to pass to cohomology. So that's the structure that we are trying to capture. Now, what is the, what's perfect sheaves? What's the category of perfect sheaves on Tate Curve? So I'll describe this in a little bit of, so there is a general definition for this category, but I'll describe a model for this category, which is, well, I'll start from vector bundles. So the objects here are vector bundles, so locally free sheaves if you want. And then the morphisms, I would like to have a chain level structure on the morphisms. So one common thing to do is to consider check cohomology. So I'll fix an affine cover, affine open cover. So in the case of this specific elliptic curve, it's a two-set cover. I'm free to choose any cover, and then I can do this business. But I'll work with an explicit cover. So this will be y not equal to 0, and this will be z not equal to 0. And then now so what are the morphisms between two vector bundles? Well, this is the check complex with respect to this open cover U and the home sheaf. Okay, so remember, since these are locally free, this is the right thing to consider. And this is a differential, the check differential, and I keep that. And I keep also mu2, which is the product. So homes can be composed. Okay, so this is a chain level category that we can define, and it depends on the open cover. I fixed this open cover, but we'll get rid of soon. Now, the statement of homological mirror symmetry involves triangulated categories. So from this vector bundle, from this category vect, I will pass to something called triangulated closure. This is a purely algebraic construction, and we will not really worry about it too much, but so basically what it is if I have, so objects of this thing is chains of vector bundles, and so this is an object of this triangulated closure, and well, it might be a little bit more complicated than this. It can have some morphisms that jump more than 1 degree. Okay, so this is an algebraic construction which makes this category, which completes this category into it's a model for the triangulated closure of this this vector bundle category. So perf of Tate is just the cohomology of this. Okay, so now the statement that we want to prove is the following. I have this symplectic category that I constructed, which I described its object as explicitly as possible, and then I passed its triangulated closure, and then we have a chain level isomorphism between this and the triangulated closure of the vector on the Tate curve. So this is what we are after, but of course, as stated, it's really abstract. It's not clear. If you're not an expert in this business, it's not clear what to prove, right? So we'll go through a much more explicit route, and this is a well-known route. So we are just implementing this route in this implementing this idea in this case. So it's the following. We consider generating sets. So this category, Fukaya category of T2Z, is a huge category. Although I described you all the objects, in general, it's a huge category. And even in this case, I told you that I'm not able to compute all the higher products. Okay, so a simpler thing to do is to find a subcategory inside this, and this subcategory will be called generating set if I pass to the triangulated closure of this subcategory, then I get an isomorphism with the triangulated closure of the whole category itself. What it means, in other words, is that I restrict my, so remember this construction of triangulated closure was, I just take some objects from my category and I consider the chains consisting of them. And then here, I'm saying that I can find a much more smaller part of this whole big category, such that it's after this passing to triangulated closure, I generate the whole. I get the same thing as the triangulated closure of this bigger category. So again, in the case of torus, this is actually very easy. So this A and B are the curves that you would expect. These are the generators of the cohomology. So I make them exact oriental Lagrangians. And what does it mean to generate? It means basically, so let me say it like this. So this triangulated closure involves, so the triangulated closure is taking, if you have two curves, then in the triangulated closure there should be another object here, which will fit into the exact triangle with your objects. And this is well known in Fukaya category. This corresponds to the Dane twist of so this object is the Dane twist of B by A. This is an example of a Seidel's exact triangle. So if I take sufficiently many copies of A or sufficiently many copies of B and apply the twists around them, then it's clear that I can get all the curves. So this is an intuitive explanation of why A and B generate this category. Okay, so a similar situation happens on the complex side. Sorry, on the algebraic side. Well, on the algebraic side, we have two distinguished objects. One is the structure sheaf, and the other one is this skyscraper sheaf at the point sigma. Remember, I had this point at infinity that I fixed, and it's not again, it's not hard to prove that this generates the perfect complexes. So maybe to be more honest, I should replace this with the complex O sigma, because I told you that I'm working with I'm working on the chain level with this objects consisting of chains of vector bundles. Okay, so this is a skyscraper shift. These are chains. This is a chain of vector bundles. Okay, so now we are getting a little bit more concrete, right? We had this big categories, but now we said that each of them are generated by these two objects. So one of them is this A and B on the symplectic side, and the other one is this O and O sigma. So let me emphasize this point. So these are chain level structures. So there is objects, there is homes between them, and there are higher products on this side, and here again there is home. So O and O sigma are the objects, and there is home between them. And then there is the check differential and the product. Okay, so our goal is to identify these chain level structures at the chain level. So that's the statement of homological mirror symmetry. So that would imply the statement of homological mirror symmetry, because once we have this chain level isomorphism, it's carried out to the triangulated closure by just algebraic construction, and then we have this chain level isomorphism. So it's now somewhat much more concrete. We have we just need to compute these things, and then see whether we can match them. So, well, okay. So if you're looking for a chain level isomorphism, one thing that would be reassuring is if their cohomology is already isomorphic, right? So it's kind of a weak, somehow simple check whether the cohomology categories are isomorphic. So what do I mean by that? So at the level of cohomology, so what do we need to check? We just need to check the following. So I construct this algebra, which is now the Floer cohomology. It's not the chain level. Between objects on the symplectic side, and then on the algebraic side, I have this again X-group computations. And I need to have that these are isomorphic as algebras. Well, this is a very simple calculation in this case. So here I'm just saying the Lagrangian Floer homology of a circle. So it's just a circle in a torus. It's just this is a cohomology of S1. Here A and B just intersect at one point. There is no differential, nothing. So this is just a K. And again here it's also the same. There is a shift of grading, which I'm not discussing, but it's there. And there is also H star of S1. It's also a simple computation to do that, to compute X of OO on an elliptic curve, and sections of O sigma and so on. It's easy to verify this isomorphism. Moreover, I just described you additively, right? But the algebraic structure is also easy to compute in this case. So this is an algebra A. So the algebra A is of this form. So A has these these generators E0, E1, U1, V0, F0, F1, corresponding to the summands. And well, E0 and F0 are idempotents. So they multiply as idempotents. And then there's two other interesting products. They're like this. In any case, I just sketched very fast this explicit algebra. So there is an explicit, I don't know, 6-dimensional algebra over our ring K, C, Q that comes out of this this A and B curves on the symplectic side and O sigma on the algebraic side. So the cohomologies match as algebras. So now, how to match the chain level structures? Well, here's one interesting observation at this level. In computing this X and the algebra structure on that, I did not use the specific form of the elliptic curve. Any elliptic curve has this algebra. So somehow, I started in the beginning that I want to match the chain level of Fukaya of the symplectic torus with the Tate curve, an explicit one. But on the cohomology level, we always get the same algebra. Okay, so this is an important point. On the chain level, it turns out the elliptic curves are distinguished. So how to understand this? Okay, so we have this algebra A. And on this algebra, on the symplectic side, we have, symplectic side, we have the algebra A, and on it we have the higher products that we haven't computed yet. And on the algebraic side, we have we also have a model. So let me say like this. So the algebraic side was given by these check complexes, right? So this model has its differential and its product. Now this what we computed here is that its cohomology is this A. Okay, so there is something called a homological perturbation lemma, which is a standard tool. And what it does is it changes a DG algebra, such as the one here, to an A infinity algebra in its cohomology. So we can trade at the chain level this one with another higher product. So let me denote it like this. So what it does is that it takes the cohomology of this DG algebra and then transfers the differential to a higher product, so that this is still in a chain equivalence. So in summary, what I'm saying is I have two ways to construct A infinity algebras, two different A infinity algebras, whose on the same underlying cohomology algebra. Okay, so this is, so I have A mu 1k. That's maybe I'll write mu symplectic case and A mu algebraic case. In fact, I have on the algebraic side I have many, right? On the symplectic side, I started from the symplectic torus, and I have this explicit geometric model. And on the algebraic side, it depends on the choice of the elliptic curve. For any elliptic curve, I have an infinity algebra whose cohomology is the same, right? So, all right. Any questions? Is this somewhat clear? Okay. Now, how to match our symplectic guy with one of these elliptic curves? Well, here a great machinery comes in, which is the deformation theory. So here is a general form of an elliptic curve. So any elliptic curve I can embed into P2. It has this Weierstrass form. Okay, so these AIs are power series in Z adjoint Q. And starting from any elliptic curve, I can consider this O and O sigma, and I can obtain an A infinity algebra. So A together with higher products from this. Okay, from any elliptic curve. So, well, the elliptic curves has this. So I described them as embedded, and then there is of course, there's a repermutation group acting on this. So let me write W for Weierstrass curves. So curves of this form, and on this there is a group acting G. So G is this subset of PGL3. Let me write an explicit. So G is this kind of matrices. So U is an element of K multiple group, and STR is an element of K. So any such equation, I can act with this matrix, and I would get an isomorphic elliptic curve. And the action of this, now this is a very elementary piece of the talk, but the action of this this group is kind of interesting in the sense that people have figured out this many years ago. So it changes A1 to this. It changes A2 to kind of this. And A3 maybe. So it changes the coefficients of the curve quite interestingly. And here is how it acts on the coordinates x and y. Okay. So this is, I mean, the explicit form is important in calculations, but it's not important for the sake of the talk. But what I want to show is somehow there's interesting transformation. So now, well, to first order, the deformation theory of these Weierstrass curves is controlled by the map from G to K. So W, which is well, A2 by this map. So which is the linearization of this group action, right? So I have this at the origin. So when I have all the AIs equals to 0, I get the cusp curve. And to first order, the deformations are controlled by this complex. So if you're in the co-kernel of this, then you can deform. You can deform. And if you're in the kernel, that's like reparameterization of the deformation. So and the picture is like so. So kind of this is a easy computation. The kernel of D, I mean D is this matrix, some explicit matrix from these equations that you can obtain, and the kernel of D is this. Sorry. Yeah, kernel of D is this. So explicit thing, and co-kernel is also so notice that I'm keeping this these ideals because it's I can. So for example, if I have a field K with different characteristics, these things are different. So now, okay, so we have this this deformation picture, and remember, I told you that I can start from any Weierstrass curve. So an element of this W, and I can obtain an A infinity structure. So let me call this A, which is the set of A infinity algebras with mu1 equals to 0, and it's A such that its cohomology is the given algebra A. So remember, I told you that from any Weierstrass curve, I can obtain an A infinity algebra with its cohomology given by this explicit A that I described, and then it has this higher product. So here's this map. There's this from any Weierstrass curve, I have this. So this set, in general, can be rather complicated, right? I'm talking about all A infinity algebras with its cohomology, a specific algebra A. But it turns out, in this case, we can prove that this map is so we can actually make this into a scheme, and then this map is an isomorphism of schemes. So this map is over this coefficients. So we have an isomorphism here. And this isomorphism is in such a way that the group action here that I described over there is intertwined with somehow there's this reparameterization of infinite algebras that's called gauge transformations, and then each group action goes to this gauge transformation. So this is kind of the main technical and kind of the meat of this the theorem that I'm describing. From anywhere, so a priori, this is a very algebraic object, so somehow like very abstract object, which we have no idea about. But from this geometric curves, we can construct pieces of this object, and it turns out what we prove is that in fact this is an isomorphism. Okay. So, and what do we use to prove that? I alluded to the deformation theory a little bit. So I told you what is the complex that kind of controls the deformations of the origin of here. So origin, remember, here is so there is a specific curve here, which is this cusp curve. That corresponds to all the AIs are 0. And here there is also a specific origin, right? The origin is the A infinity algebra whose underlying cohomology is A, whose higher products are all 0. Right? There is a formal one. So there is A dot here, which is called the formal one. So both spaces actually are based. There's a specific point. And it's not hard to show that this cusp curve, after I do this whole construction, I told you how to construct the infinity starting from a Weierstrass curve. The cusp curve gives me the formal one. And the reason for that is because this cusp curve has if you restrict this group to the k star, okay, so this k star preserves the cusp curve, and then you can use that to, in terms of, it's not hard to use that k star action and together with some grading information to prove that the cusp curve corresponds to the formal one. Now the deformation theory of this cusp curve is controlled by this complex, at least to the first order, and the deformation theory of A infinity algebras is controlled by something called Hochschild cohomology. So here we have a Hochschild chain complex of the algebra A, and then here Hochschild chain complex of the second one. And what we show is that this map induces a map of deformation theories. Remember, I already told you that the origins are going to each other, and now the deformation theories are related. And then this map is a quasi-isomorphism. So this is over any field, or even so from which you can conclude ZQ. So this part it requires an explicit computation of this Hochschild cohomology. So, and then that's a very beautiful story, but maybe I won't have time to explain it too much. So what do we need to do? So we have this A. Remember, this is an explicit associative algebra. So one way to compute Hochschild cohomology of A is to go through the definition, resolve via projective resolution very algebraically, and compute it from a projective resolution. So that's what we did a couple of years ago, but now we have a much better understanding. Remember, this is a non-commutative algebra, so it's not always easy to compute Hochschild cohomology. What we know is that this algebra A is the one that corresponds to the cusp curve. Okay, so cusp curve is formal. So what we can conclude from this is, so I'm saying it very quickly, but this is a Hochschild cohomology of the cusp as an algebraic variety. So now we turned this story to a commutative story, and then this can be computed. In fact, it's not hard. So you compute exactly, and then you match. So you see HH2 and HH1 is exactly this kernel and co-kernel, which I erased unfortunately, but they exactly match. Okay, so finally, so now I described you this and the method of how we show it, although maybe it was too fast, but what we show is that this abstract set of A infinity algebras with a fixed A is all covered by these elliptic curves. Now, the symplectic side, the Fukaya category of the torus itself, I told you it gives you an A infinity algebra with cohomology. So it gives me a point here. So here I have a point P, which is the symplectic torus. Okay, so I have this point but I want to determine which elliptic curve hits this point, right? That would end the whole story. So this is not this also we do. So how do we do this? So this is the last part of the talk. This is in some contexts it's called computation of the mirror map. So, so which elliptic curve hits the symplectic torus? So okay, so here's how you do. So if you remember, we know now by this abstract theory that A and B are, so this category is quasi-isomorphic to some, so O and O sigma of some elliptic curve. Okay, by this abstract deformation theory, we concluded this. Now we want to determine which elliptic curve. So, well, if you know O and O sigma, then you can reconstruct O and sigma, because you know, there is this exact triangle, and then iterates of this exact triangle reconstructs these line bundles. Okay, remember this is at the chain level, so we have all this information. So, but if I reconstruct O and sigma, then I can reconstruct the homogeneous coordinate ring, which is this. But if I reconstruct this, then I can reconstruct the equation of the curve, because you know O3 sigma gives me an ample line bundle and it embeds into P2. So there is a standard, you know, you can pick coordinates and then recover the equation of the elliptic curve from this ring. So that means that the chain level information on this O and O sigma recovers the whole curve. Although remember, its cohomology didn't recover anything. It was always the same for any elliptic curve. But now we know that our A and B corresponds to this at the chain level. That means this thing is isomorphic on the symplectic side to HF A, tau A, and B. So now we transferred this, you know, the computation of the equation was in related to this ring, and we transferred that to the symplectic side. Now on the symplectic side, I can compute this ring by counts of holomorphic triangles. I told you I can compute holomorphic triangles. It turns out one can compute this very explicitly and then recover the equation of the Tate curve. Okay, so I think this is the end.
So you don't